Hey, doing a quick test of sound input, and I'll actually turn on my video briefly just to see if that broadcasts properly. All right. Harsh, if you're watching this or you're hearing this, let me know.
Yeah, it's working pretty well, Erinn. Yeah.
Okay, perfect. So you can see and hear me okay?
Yeah.
Great. Okay, I'm gonna turn off my video and sound for now until we're ready to get started so that nobody has to listen to me drinking my coffee, and we'll get going in about 10 minutes.
Perfect. Thanks, Erinn. I'm also waiting for this.
Can you also see the screen that I'm sharing already?
Yeah, I see your screen.
Okay, perfect. Thanks. We're going to get started in just about a minute or so. Give it just one more minute for any stragglers to come on in, and then we'll get this party started.
Perfect. Thanks, Erinn.
Okay, I'm going to go ahead and get started, and people can just join us whenever they want if they would like to, or if they don't want to, I guess that's up to them. And to those people who are choosing not to join us, I'm sorry that you're missing this right now. You might be watching this on video. Anyway, we'll just start kind of with a brief overview of what we're going to be talking about today. We'll kind of dive right into it, and we'll see how things go. We'll probably pause for questions periodically. I'm going to try to do them at fixed points during the presentation, just so that we don't break up the flow too much. But if I see questions that are very topical and relevant to what I'm discussing at any given moment, I will try to address them as they come in. I'm going to do my best to keep an eye on the questions list while I'm talking about stuff. I want to apologize ahead of time if some of the early part of this presentation is kind of fairly elementary and review for a lot of folks. My expectation is that most of the people interested in watching this are not super experts on probability and statistics kind of stuff, because if they were, they probably are already acing a lot of the probability-based SRM problems I come up with. At least that's my assumption, but it's also important to understand a lot of the basics just to really see where some of the formulas come from, some of the logic, and the more you understand the basics, the easier it is to kind of come up with ingenious solutions as you go along. So we're going to see how this goes. So as I mentioned, we're going to kind of start with the basics and some of the not so basics. Spend a little bit of time talking about statistics terminology and some of the basic applications. We'll talk through a few fairly detailed non-contest examples, just kind of things in real life where some of these concepts might come up. Spend a little bit of time working through them so that you can see just how some of this stuff actually goes into practice. We're going to talk about a couple of recent problems, two of them in fact, both originally written by me, that are reasonable enough to work through. We're not going to go through the actual code to solve them because that's already available online. You can find people that solve them. You can find the reviews and the editorials for those contests, but we are going to talk about how you break down the problem and how to solve them. And we're hopefully going to leave some time at the end for questions and a little bit of open discussion. So with that, let's kind of jump right into it. With the basics, we're going to talk about simple probability, just very, very basic, what's the chances of a single event happening? Move into a little bit of talk about multiple events, what's the chance of A and B happening, or what's the chance of A or B happening? We're going to talk about dependent versus independent events. Those are basically just things where the result of one might influence the chances of another thing happening. We're going to talk about permutations and combinations, which are important for counting. And we're going to get into binary probability distribution, which is kind of our first heavy-duty formula that we're going to get to look at. So let's continue along. I should mention I do have a couple of points in this presentation where I kind of am planning on taking a little breather for a minute or so, just so I can catch my breath, take a little bit of my coffee, and give everybody a chance to just, if they need to stand up for a second or whatever, not miss anything. I expect this to go at least an hour. We do have 2 hours blocked out, so we're gonna play it by ear and we'll see what happens. All right, simple probability. The simplest thing we're talking about, what are the chances of something happening? That sounds almost too simple, but that's really what we're getting at. And we want to talk in terms of simple because that's what is easy to understand. The probability of something happening should be between 0 and 1. If it's not, there's probably an issue. and it is a real number. It's obviously continuous. 0 means something is definitely not happening. 1 means it absolutely is happening. Anywhere in between tells you essentially the chances that something is going to happen. The higher the value, the more likely it is. And the way you calculate simple probability, you count up the number of ways to get the result you want, divide by the total number of possible results. Some of the most simple examples of that, if you flip a coin, assuming it's a fair coin that's weighted evenly, you've got heads or tails. There are 2 possible results. Number of ways to get a head, that's one. There's 1 way it can come up on heads. Out of 2 possible results, your probability is 1/2. And of course, that's what I just described. That's probably the simplest and most common example you hear first off for probability. If you draw from a deck of cards, chances of pulling a spade, there's 13 spades in the deck out of 52 cards in the deck, so your chances are 13 out of 52 or 1/4. Chance of pulling an ace, there are 4 aces out of 52 cards or 1 in 13. Okay, that's the simplest thing. Now let's say we have 2 different events and we want to see what's the chance that both of those things happen. It's actually not that hard. Multiply the probabilities together. Now, note I am saying this, those of you who are more familiar with some of the more complex problems know that there are some nuances to this, and we'll get to those. This is just for very simple situations. Simple example, what are the chances of flipping heads twice in a row if you've got a coin that you're going to flip twice? And the answer is simply 1/2 times 1/2 equals 1/4. Now, what are the chances of multiple events where either one of them happens? In general, you're going to add the probabilities together. And a good example for this is drawing a card out of a deck and getting one of 2 different suits, either a spade or a heart. 1/4 plus 1/4 equals 1/2. Something important to note here is that getting a spade or a heart are things that can't happen at the same time. So we're pretty safe here because there is a situation where you need to be careful. Specifically when you're dealing with the either or for things happening. Let's look at the problem of you flip a coin twice and at least one of them is a head. Now you might think that, oh, 1/2 plus 1/2 equals 1, but obviously that's wrong because it's entirely possible to flip tails both times. So why does that come out wrong? We need to account for the fact that both could happen at the same time. Simply adding them together, we're double counting in the situation that both of them happen. Kind of a funny example that I actually read in a mathematics textbook many, many years ago. Suppose a weatherman comes and is giving the forecast for the next few days and says, well, tomorrow we've got a 50% chance of rain, and the day after we've got a 50% chance of rain also. I guess that means over the next 2 days we've got a 100% chance of rain. Obviously, that's not accurate, and anybody who's mathematically inclined will certainly realize that pretty much immediately, probably laugh at the weatherman's expense, and realize, of course, he's not considering the fact that maybe neither day rains, and not accounting for the fact that if both days rain, we've double counted that. So how do we deal with this sort of situation where we're not being careful? There's an alternative calculation approach for the either or scenario. The probability of at least one thing happening out of a selection of possible events is 1 minus the probability of all of them happening, because at least one is exactly the, you know what, I actually just realized I made a small mistake here. So we're going to just kind of skip this slide and I'll talk about it verbally instead. That should say the probability of none of them happening, not all of them happening. My apologies. Let me draw a little quick annotation here because I made a small mistake. You see, this is what happens when I don't have enough coffee when I'm putting one of these together. I appreciate all of your being patient with me. Okay. So the probability of at least one event happening is 1 minus the probability of none of the events happening. Now, in the case of coin flips, the probability of none happening, that is, we flip two tails, is 1/2 times 1/2 is 1/4. And then the probability that at least one happens would be 1 minus that 1/4, and is 3/4. So 3/4 is in fact our correct answer. I just kind of didn't use the right words to describe that. Again, my apologies for that. Thanks, everyone. All right, let's move on. We're going to pretend that that mistake never happened, right? All right, thanks, everybody. Oh, excellent. The annotations still show up when I change slides. Let's clear all of the annotations. There we go. All right. Okay, let's talk a little bit about independent events. I did mention we're going to talk about independent and dependent events. This is where things start to get interesting. Independent events means the results of one trial does not affect future events. Some common examples of this: flipping a coin or rolling dice. Allegedly, it was Albert Einstein who said this. I'm not sure if the quote is accurately attributed to him or not, but the phrase "dice have no memory." You may have heard of something called gambler's fallacy. If you're constantly throwing dice and always getting a bunch of 3s and 4s, you might think either that A, you are more likely to get 3s and 4s because those dice just like 3s and 4s, or you might think B, you're due to finally roll a 5 or a 6. Assuming we're talking about fair dice, if we're talking about loaded dice, that's a little different. But if we're talking about fair dice, that's obviously not true. Each individual roll is its own event and has its own chances of things happening. What happened before or what comes after do not affect each other. Another good example of independent events is drawing a card out of a deck with replacement after. That part is important because some of the early examples for simple probabilities I was giving you, the denominator of my fraction was 52. We're assuming all 52 cards are in the deck. If we're drawing cards without replacing them, then there's not going to be 52 cards in the deck anymore. So with replacement after or without replacement is an important phrase to look for when you're talking about different scenarios. That's going to tell you whether you're talking about independent or dependent events. Now, of course, independent events means they don't affect each other. Dependent events, as you might imagine, is exactly the opposite. The result of one trial does affect future events. Some common examples where this comes up: drawing 2 cards without replacement. So for our first draw, let's say we're looking to draw a spade, we might have a 13 in 52 chance of grabbing a spade. In fact, well, we do have a 13 in 52 chance of grabbing a spade. If we draw a second card looking for a spade again, we've now got a 12 in 51 chance of getting it because there are 12 spades left in the deck out of 51 cards. That second event depends on the first one. Pulling marbles out of a bag is another common example. I mentioned this one specifically here because that is one that actually is used in a lot of programming contests. Particularly, I've written any number of problems over the years that actually talk about pulling marbles out of a bag, usually red and blue marbles, but you can use whichever colors you like. That doesn't affect things. And of course, the probability for the second pull is different than the probability for the first pull. Even if we are doing what seems like the same thing, the conditions that under which we're making that pull are different, so we need to account for that. Okay, we're going to talk a little bit now about permutations and combinations. These are not specifically probability items, rather they are combinatorics terms. Combinatorics is kind of the fancy word for counting. I did say right at the top of this presentation, simple probability is number of ways something can happen divided by total number of possible events that happen. And I said the real trick is counting those values properly. That's where this starts to get important. As I say, these are ways of counting things. A permutation means the order matters, and a combination, only the selection of items matters. Some common examples for this permutation: if you are opening a lock like you would find on a padlock on a locker or a safe, the order of the numbers actually matters. Combinations, oddly enough, because they usually call them a combination lock, they're actually permutation locks, but combination means only the things you select matter. When you are putting together your dinner and you're putting food on your dinner plate, peas and carrots is the same thing as carrots and peas. So the order in which you place things on your plate doesn't really matter. If you are dividing people into cars because you need to go somewhere, it doesn't really matter if you're taking Amy and Sue with you or if you're taking Sue and Amy. It's the same selection of people. So the simplest example of a permutation is how many ways can n things be ordered? A common problem that sometimes you get, especially even in elementary school, very early ages, is how many ways can you rearrange the letters in your name? And that's, of course, at that level, most students, maybe some of the folks here would have figured this out at an early age. If you're interested in programming contests, there's a good chance you did, are going to just start writing out all the different ways they can scramble the letters of their name, possibly without any rhyme or reason, without any ordering to it, but they're just going to try to write them all out. Some folks might actually figure this out mathematically. And the answer, of course, is n factorial. Just in case anybody's not familiar, factorial is simply the product of whole numbers 1 through n. We could get into a discussion of it being a specific case of the gamma function, but we're not going to go that far today because it's not really relevant, although it would be a fun rabbit hole to go in. Okay. Now, a more specific example here, how many ways in order can you pick R items from a set of n? So this is where the order matters, but we're not selecting everything from a group, we're only picking a certain number of those items. And the answer is n times n minus 1, and so on, subtracting. The reason for that, let's say we've got 10 marbles in a bag, different colors. On our first pull, there's 10 different things we could pull out. On our second pull, there's only 9 different marbles we could pull out, so that's our n minus 1. On our next pull, there's 8 different marbles, that's n minus 2, and so on, for however many we're going to pull. And in fact, we can simplify that formula as n factorial divided by r factorial. You might be starting to see why programming and writing code starts to become more interesting than doing this on paper, because a lot of these calculations are not that easy to do by hand and are much less time consuming to do in code instead. Another example of terminology, NPR, where you have both the N and R as subscripts, is just another way of writing the number of ways of selecting R things from a set of n in order. And again, that's n factorial divided by r factorial. Fairly simple formula, but very, very good to keep in mind. Now let's talk about combinations. If we're going to select things without caring about order, then the answer is n factorial divided by r factorial times n minus r factorial. Some other terminology for it, NCR, where the n and the r are actually subscripts. Sometimes you see them in parentheses with the n over the r in kind of a 2-by-1 matrix sort of format, is n factorial divided by n minus r factorial. If you're wondering where that formula comes from, you might notice the n factorial divided by r factorial looks suspiciously like the permutation formula, and in fact, it is. Now, so there's our permutation formula. Why are we dividing by n minus r factorial? And the reason for that is that we don't care about the ordering. So by dividing by the, yeah, you know, I made a small mistake in what I was saying again. Let me try this. Try this again. Here is our, this is actually our permutation formula. I apologize, that's 2 mistakes I've made in this. I may, I'll correct these things before I actually publish the slide deck separately. I have a few little minor typos in here. N factorial divided by n minus r factorial is our permutation formula. We divide also by r factorial because the order of the things that we selected does not matter. And of course, r factorial is the number of ways we can sort those. Binomial probabilities. This is a specific case where we actually have to put a few of the concepts we've talked about so far together. If something has a probability of p of happening, what are the chances that happens r times out of n trials? Now, we talked early on about throwing heads twice in a row when you flip a coin. What happens if we make it more than twice in a row? Let's say we want to flip a coin 3 times. What are the chances we get exactly 2 heads? we're looking at what's called a binomial probability. To solve this, start with the notion that we let Q equals 1 minus P, essentially the probability that something doesn't happen. If we're talking about a fair coin, both P and Q are in fact 0.5. We could be talking about something that's not necessarily an even chance though. Maybe we're talking about an unfair coin. Maybe we're talking about with dice rolls, the chances of rolling a 1 where it would be 1/6 and 5/6. What we get then is called the binomial distribution formula. I'm going to annotate some of this as I talk about it because I think there's a lot of interesting stuff here. It's the number of combinations of n items where you select x from them times p to the x times q to the n minus x, which equals the combination formula times p to the x times q to the n minus x. So why is that? Let's look about why this actually happens. So we're talking about flipping a coin n times and x of them being a heads. P to the x is essentially the probability that x of those trials come up on a head. Q to the n minus x is the probability for the other trials to come out as a tails. So why do we multiply by the number of combinations of picking x things out of n? Well, the reason for that is which of the trials came up on heads? When we say, imagine that heads comes up twice out of 3 flips, we could be looking at a couple of different scenarios. We could be looking at HHT, HTH, or THH. So there are in fact 3 different ways to choose 2 of the flips that ended up on heads. That's why the number of combinations is multiplied by the probabilities. And we come up with this formula here. You've probably seen this before, but it is good to know this because it is a nice little shortcut for being able to calculate a lot of these things. And yes, I did pull this formula off of the site rather than retyping it up myself. I'm actually kind of glad I did that because it avoids me making a silly mistake. Okay, we're going to pause for a minute, catch our breath for a moment. We've been at this for a little over 20 minutes already. So I'm just going to go on mute for 1 minute, grab a little bit of my coffee, and then we'll move on. Meanwhile, if anybody has any questions on anything that I've talked about thus far, feel free to post them in the Zoom questions, and I will do my best to breather for 1 minute. Okay, we're going to continue in just a moment here. I am coming back alive. Drank a little bit of coffee. Hold my breath for a second. Hopefully all of you are still enjoying watching this. Despite a few little typos I had there, my apologies, sincerely, really and truly. Again, I will correct those before I publish the slide deck online after this. Hopefully nobody hates me too much. Let's see, I'm actually just catching up quickly on the chat that I'm seeing. I didn't realize that chat was separate from the questions window. I do want to make sure I follow, okay, I want to make sure I follow everything that anybody is saying and make sure that anybody's questions are covered. And it looks like we're pretty good for now. All right, so let's move on. Let's talk a little bit about statistics, terminology, and application. One of the things I did want to cover, because statistics and probability are so closely related, is some of the statistics side of things. I will mention that statistics doesn't come up directly in the algorithm contests, the SRMs, not quite as often. However, it does come up in marathon matches, so it is at least worth mentioning and having some understanding if you ever want to move over to that side of competition. We're going to talk about the notion of an expected result. That is, if I do something, what do I expect is going to happen? Expected number of trials. If I'm looking for a certain result, how many times do I think I'm going to have to try until I get that result? Simple things like the mean, median, and mode. Those are other simple things you've probably heard before, but it's good to make sure we know them. Standard deviation and the bell curve. Very simple discussion on that. We're not going to get into too many details, but enough so that at least you have some understanding of what it is. All right, expected result. This means the number of occurrences or total payout you would expect to see on average for some number of repeated trials. Simple example, after you roll a dice n times, how many times do you think you're going to see a 1? The answer is simply 1/6. The reason for that is any given roll has a 1/6 chance of being a 1. We're assuming a 6-sided die here for those of you who are tabletop role-playing game folks and are familiar with D8s and D20s and all that mess. I should have probably specified that, but so you simply multiply your n trials times a 1/6 chance for each. N/6 is the expected number of ones you're going to see. Now, does that mean you're definitely going to see that? Of course not. It means that's the most likely expectation you're going to see. It means over a whole lot of trials, the number of occurrences is going to tend toward that number, but that does not mean it's exact or definitely what you're going to have at any given point. Suppose you have a bag with 1 blue marble, 3 red marbles, and 6 black marbles. I told you I love marbles and usually red and blue are my favorite colors for these. Well, here we go. You win $10 for pulling the blue marble and $2 if you pull a red. What is your expected payout for a single pull? Now, some of you might be able to look at this and kind of work it out pretty quickly. But let's actually just go through and work this so you can see where the numbers come from. To calculate payouts, multiply the chance of each event by the payout for that event and then add those values together. Pretty simple. The chances of blue, red, and black are 0.1, 0.3, and 0.6, 1 out of 10, 3 out of 10, and 6 out of 10. I'm hoping we all understand converting fractions and decimals and percentages and that kind of stuff. So we multiply 0.1 times the $10 payout plus 0.3 times the $2 payout plus 0.6 times $0. We get an expected payout of $1.60. And that's all we have to do. So if it costs you $1 to play this game, it's actually a pretty good game to play, right? If it costs you $5 to play this game, it's probably a very bad idea to play this game. We'll talk more about lotteries a little bit later, but just to give you a clever example for now. Expected number of trials. That's when we ask questions in the form, how many times will you have to do an event to reach an expected result? And I found another typo. Gosh darn it. If I told you how many times I've gone through this looking for typos, you would think I would have done a better job by now. My apologies. How many times do you roll a 6-sided die until you're going to get a 1? Now, you might instinctively say, well, on average 6 times, and in fact that is correct, but let's derive that and see where that comes from, just to make sure it's clear. Let X be the expected number of trials you're going to have to do to get the result you're looking for. There's a 1/6 chance that's going to take you exactly one trial to get that one coming up. There's a 5/6 chance that you're going to fail the first time, and after that, you are going to need X more trials until it happens. Notice that we have X actually depends partly upon the value of X. I smell an algebraic equation here. So we in fact solve it. X equals 1/6 times 1 plus 5/6 times 1 plus X equals 1 plus 5/6X gives us X equals 6, as we expected. Or perhaps we expected, but it's good to actually work through and confirm this. Understanding how we derived this is actually really useful for a lot of problems that ask about what's the expected number of times you're going to have to do things, because sometimes it's not just a simple 5/6 chance. Sometimes it's some more complicated value we have to calculate. So knowing how this calculation takes place is actually really good to keep in the back of your mind. And of course, in general, if an event has a 1/n chance of happening, you can expect it to take n trials to happen on average. Now, here's an interesting question. What are the maximum number of trials it's going to take to get that one? Well, there actually is no maximum. It is entirely possible you will sit there rolling that die indefinitely. You will be old and gray, the universe will have died a heat death, and you will still be rolling that die. Don't ask me how you're going to be doing that if the universe has already died, and you've never come up with a 1. The chances of that happening are vanishingly small after a certain point, but it is possible. That's why you might think, oh, well, there's a 1/6 chance. Sometimes it's going to take me 6 times, sometimes it's going to take me 1, so on average it's going to take me 3 or 4 times. That's why it's not that. There is a possibility of it taking much more than 6 tries. It's a small possibility, but it definitely is there. So the average is in fact still 6. Let's talk a little bit about mean, median, and mode. You'll hear these come up in statistics a lot. When we talk about average, average is kind of a not very precise term that's used a lot, but we're usually talking about the mean. You do want to be careful though and make sure. In general, if it's not specified otherwise, then when you see the word average, it's probably mean. Mean is simply the sum of a bunch of values divided by the number of values. So a common example, if anybody is into the sport of bowling, we talk about one's average. You scored 150 the first game, 160 the second game, and 140 the third game. Your average across those 3 games is 150. Median is the middle value in a sorted list, or the mean of the 2 middle values if it's an even number. So you can sometimes have a bunch of data points, maybe the values 1, 2, 3, 5, 8. We'll do the Fibonacci values, why not? The median value, the one in the middle, is the number 3. If you were to calculate out the mean, however, the average, it would actually be a little bit higher than 3 because some of those larger values would push it up. And mode is the value that is most common in a list. Sometimes there can be more than one value that's the mode. If you had a list of numbers 1, 1, 2, 2, 3, then both 1 and 2 are the mode. If you had a list of values 1, 1, 1, 2, 3, then it's just 1 is the mode. Let's talk a little bit about standard deviation and the bell curve. Standard deviation is actually calculated by the formula given here. It is the sum of each value in a data set, subtract the mean from it, square it, divide that by n, then take the square root of the whole thing. It's kind of a measure of how spread out a set of data values is. We're not going to get more into this too much today because it goes beyond the scope of where I was really hoping to be with this, but it is good to at least be basically familiar with these terms. A lot of real world data is what's called normal and fits this type of model where it's actually a bell curve. And the reason I mention all this, this approach is often used when we're generating data for marathon contests, where we want values that are kind of around a certain value or within a certain range, but tend to stick close to one particular set of values. Most of your data points are going to be close to the mean. They're going to be near the average, and the further away you go, the less data points there are. There's no necessarily upper or lower limit, but the further away you are from the average, the less common it's going to be. One of the common examples I see for this is testing people's temperature. Now, a lot of folks have heard that normal human temperature is 98.6 degrees Fahrenheit. I forget the exact Celsius conversion for that off the top of my head. But we might ask ourselves, well, how do we know that that's normal? And the answer is simply it comes from a lot of measurements that doctors did well over 100 years ago on who they believe were patients that were healthy. They did a whole bunch of measurements and saw roughly where people looked, and that was kind of about the average. Around 98.6 people were healthy. So is there anything magical about that number? Not necessarily, but it does appear to be the most common value right in the middle of where everything falls. Here's a fun little exercise. We're not going to work through this in too much detail, but just something to think about because I think it's interesting. You've all seen Pascal's triangle, hopefully. As you go further down Pascal's triangle, the values will increasingly approach a bell curve where it is, let's do some annotations on here. Near the edges, you have very, very small values. But in the middle, you have very, very big values. And as you still have somewhat big values near the middle, but as you get further away, it drops off very quickly. So the question is, why do those values actually look like a bell curve? I'll give you one hint. In the study of combinatorics, again, that's counting things, a common way to derive formulas is to count the same thing in two different ways. So we know that Pascal's triangle, each number is the sum of the two numbers above it. Imagine that going from, you start at the top, right up here, here's where we start, and we're going to go down to the next row. Suppose we make a coin flip to determine whether we go to the left or to the right. Heads we go left, tails we go right, for instance. Any given point in the triangle is the number of times we've rolled a certain number of heads and a certain number of tails. In this second row here, rolling one heads gets you on the left, right here. Rolling one tails gets you on the right, right here. In the third row, two heads, one heads, one tails, two tails. So in fact, the bell curve and Pascal's triangle are a pretty good example of the binomial probability distribution. Fun stuff. Okay, clear that off, move on. Talk a little bit about expectation where there's decision-making involved. This is another example where things start to get interesting. And when we talk about decision-making, you might, in your mind, convert that to an if-then statement. And if so, good job, because you're seeing why programming is part of this. Obviously, when we're talking about decision-making, we mean that we're choosing from multiple options. And it's important that we know the expected result from either choice. Expected result, again, when we're talking about probability, does not mean definitely what's going to happen. It means what we think is going to happen on average. And what this means is that playing optimally means picking the choice that's expected to be better. Now, it may not always be better. Sometimes picking the option that is less optimal, you might get lucky and it works out for you. Sometimes picking the better option, you might get unlucky and it doesn't work out for you. But it means picking the option that's best most of the time on average. So a little example, and this is one that you can kind of just think about on your own. Which game is mathematically the best one to play? And here's some hypothetical options. A game that costs $1 with a 1 in 10 chance of winning $8. A game that costs $2 with a 1 in 15 chance of winning $15. Or a game that costs $3 with a 1 in 4 chance of winning $6. Now, I'll give you a little spoiler. All of these games are losing propositions. If you've ever played any kind of a lottery, been in a casino or anything like this, you know that there is no game you're ever going to play where you are on average going to make money. Those just don't exist. Because what casino in the right mind would give away money, right? But the question is, which of these options is the best or the worst? Now, you might quickly look at things and think, oh, well, in option 2, we can win $15. That's the best one. That's the one I want to play. Or you might think, oh, option 3 looks great. There's a 1 in 4 chance of winning. That sounds like the best. I'll leave it as an exercise for whoever wants to play with it, to actually work it out and figure out which one of these is actually the best one to do and which one's the worst and why. We're gonna catch our breath a second again. I'm actually not gonna go off camera this time since it hasn't been that long, but I'm gonna have some of my coffee. I apologize, you get to see me drink coffee. You might remember that programmers are simply tools that turn coffee into code and mathematics. It's true here as well. We'll kind of continue on. At our next breather, I might actually go off again for a minute to catch my breath, but for now, I think I'm good to keep going. And I don't see anybody complaining about that in the chat, so that's good. So either you have all fallen asleep from watching this, or you're good with my decision to keep on going. So here we go. Let's talk about a few worked examples with a little bit more detail that are not contest specific. We're going to talk about lottery drawings, again, because it's probability has everything to do with them. We're going to talk about a problem called the birthday paradox. Oh, Topcoder team says, I am up and awake. All right, I'm guessing that's probably Jesse or Harshit, one of them. Thank you for being up and awake and watching this. We're going to talk about a problem called the birthday paradox. Oh, good. I'm glad to see other people are awake and watching and enjoy. I'm going to assume you're enjoying. If you're awake and you're still on, there are still, let's see, 27 people here. That's good. Okay, so talk about lottery drawings, the birthday paradox. We're going to talk about scratch tickets, which of course are a type of lottery, but they're an interesting one because there's a lot of data I was able to pull online for these. Okay, lottery drawings. Usually, at least in the United States, I don't know if this applies all over the world, but there's some number balls, 1 through N, and the lottery selects R of those balls. On your ticket, you also select R numbers. Now, the odds of winning, of course, are 1 out of the number of ways to choose R things out of N. Notice I say select. I don't say that the order matters. That's how we know we're doing a choose, not a permutation, so it's a combination. And we already covered the formula for this earlier, so that's fairly straightforward. Now, if you were to look at a lot of lotteries, at least again in the US, oftentimes there's maybe 60 numbers that you choose from and you choose 6 of them and you could win $1 million. Of course, if you work out the math, you would see that the chance of actually winning that is much longer odds than 1 out of 1 million, which is why in general, the lottery is not going to be a winning proposition. However, a lot of people enjoy it anyway, simply because they think it's fun to dream about what if they win. It's only $1 to buy the ticket. What I can say, mathematically speaking, is that somebody who buys a lottery ticket once a day for their entire life, mathematically speaking, is going to spend a lot of money and most likely isn't going to make a whole lot. That doesn't mean it's not fun, and that doesn't mean there's anything wrong with doing that as long as you're aware of what it is going into it. But that is mathematically how it works, because of course lottery drawings are a source of revenue for governments, and that's okay. Let's take a little bit more complicated example. How about you only match some of the numbers, but not all of them? Maybe you match exactly 3 of the numbers. Let's say that PR probability is the number of draws that match 3 over the total number of draws that are possible. The number of winning draws that match 3 out of the R selected numbers would be the number of ways to choose 3 of those R multiplied by the number of ways to choose the rest of the numbers from the non-winning numbers. So you can see there's a reason that matching only 3 numbers out of 6, for instance, would pay a lot less of a prize than matching all 6, because there's a lot more ways to win, so the chances are much better that you're going to win. Note that the total number of lottery draws is still the number of ways to choose R balls out of those N. Okay, let's talk about the birthday paradox. You've probably heard this problem already. It actually comes up in a lot of interesting places, which we'll talk about a few of them just for fun. But the birthday paradox basically is a problem. Given N people gathered together, what are the chances that at least 2 of them share a birthday? Right off the top of your head, you might think, oh, well, you're gonna need a whole lot of people gathered together before you're gonna have any that are gonna have a birthday together, right? Certainly, right? So what's the minimum value of N for which P is greater than 0.5, where the chances are better than even that at least 2 people are going to have a birthday. So let's calculate the odds of at least one shared birthday. We might remember when we're talking about a probability calculation of at least one of certain things happening, the best way to do it is to do 1 minus the chance of it not happening, because it's much easier to calculate that correctly. So what are the chances of no shared birthdays? Do the annotation pen for this, just to make sure it's clear. The first birthday, we can select any day of the year out of all of them. The second person, there's only 364 days left to select out of 365, and so on. The next person would be 363 days that we could select, next person 362, and so on. So the answer turns out to actually be somewhat surprising if you do the math on this. Get 23 people in a room and you have better than even chances that at least 2 are going to share a birthday. The reason for this, even though that might seem kind of counterintuitive, when you have 23 people in a room, there are a lot of different pairs of people that could actually be sharing a birthday together. In fact, there are 23 choose 2 pairs, which is 23 times 22 divided by 2, so 23 times 11, 253. Did I do my math right on that? I think I did. If I didn't, feel free to correct me. But essentially, the more people you get together, the more possibilities of there being a collision. And in fact, the rate of growth of collisions gets much, much higher. The reason I mention as a real world example why this problem is important, a lot of forms of information security and computer cryptography rely upon non-discovery of certain hidden values. In some cases, it's possible to actually search for values that match up with each other without having to search through all that many different possibilities. It's known as, in kind of hacking and reverse cryptography, known as the birthday attack, where you simply look for 2 values that work properly together and find that, in fact, it is possible to do that. For anybody who's heard of various different hashing algorithms, which basically is a way of just kind of generating a small value from a very large piece of data, theoretically, it's very hard to come up with something that's going to match the hash. But if you employ the birthday paradox, it doesn't actually take as many times as you might think to randomly try and eventually get something that matches. Just like with people in a room, it doesn't take as many people as you might think to all be in the same room before you're going to get at least one birthday that matches. Now let's talk a little bit about scratch tickets. For anybody that doesn't know, a scratch ticket it's another form of lottery ticket, very common in a lot of countries, especially in the United States. I see them all over the place. Usually there's some sort of little game with it or some sort of goal that you're supposed to do when you're scratching off. In reality, each ticket that you get is already a winner or a loser before you do anything with it. There's nothing about how you scratched or anything like that that has any effect on the gameplay whatsoever. But the notion of, uncover 2 values that match each other or find 3 of a kind and you win, just kind of make the game seem more fun and make it seem as though there's something happening, gives you a sense of drama, that kind of thing. Again, it's entertainment value, so there is something there. They sell for various different values. Some of them sell for $1, $2, $5. Usually the higher valued ones have bigger prizes, this kind of thing. The chances of winning do depend on the individual ticket type. And of course, because it is a form of revenue, they're all theoretically losing wagers. On average, you're going to lose money spending them. However, some of them are better than others. If you're going to be losing money on this kind of stuff, you often are better off at least trying the one that is going to lose you less money, right? Sure. This is an actual example I pulled from the New Hampshire Lottery, one of their games. I did not pull the entire table, I just pulled enough so that you could see. At least the United States, and again, probably most countries, the laws are written such that they do have to publish the odds of winning so that you know what you're getting into when you play. So for this particular type of scratch ticket, you could win $1, $2, $3, $5, or $8. It tells you how many total tickets are printed with that prize, and it tells you the overall odds of winning that particular prize. Okay, so we've got some good numbers here. And if you are remembering what we talked about expected payout and mathematical expectation, you can see where we're going with this. We can actually calculate how good of a scratch ticket is this. You might remember our formula for mathematical expectation is the probability of something happening times the payout from that happening, then add together all those different things, and that gives us our total payout. So we can actually put this together into a little spreadsheet where we multiply what you win times the odds of it happening, 1 out of whatever, and that gives us the expected payout for that particular event. Add those together, gives us our total expected win. And in this example here, again, with the caveat that I did not copy the entire table, so it's actually a little bit low compared to reality, but serves fine for the example. Our total expected payout for that ticket that we bought for $1 is 40 cents. So in fact, we can see clearly and mathematically that we are losing money on it, but now we know exactly how much. Okay, we're going to catch our breath one last time before the last section where we actually talk a little bit about some real problems that we've had. For this one, I am going to mute for a second. I'm going to stop my video for just a moment. Be back in about 1 minute. It's been 20, 25 minutes since our last break. So we're going to do that once more. And yay, problems, bring them on. Okay, yeah, that Harshit is excited about that. All right, be back in just about a minute. Thanks. Okay, we're going to start up again. I apologize, that was actually probably more like 2 minutes because I really am needing my coffee. And I think we're going to talk about 2 problems now. These are both fairly recent, that's why I actually chose them. They're also simple enough that I should be able to describe them without too much trouble here. I have done some other problems in days gone by, some of which have been frankly brutally difficult and made some people mad. They're more interesting problems, but they're also way more complicated than I can describe in a webinar format. So I kind of shied away from some of those. But hopefully we're going to see how some of the concepts we've been talking about play into actually solving these problems. You might remember having seen any of these if you've been doing a lot of SRMs lately. And those problems, of course, are card draw points and card draw game. You see, once you see card draw, there's a good chance you know that there's going to be some sort of probability, something coming up with it. And in fact, that is the case. In the problem card draw points, we've got a deck of cards of various values. And in fact, we're given as input how many of each value card are in the deck. The way the game works is you can keep drawing cards for as long as you like, and the score is the total of all the cards in your hand. However, if you ever draw a duplicate of a card you've already got, it's game over and you score a 0. That makes this interesting. And of course, the question is, what's your expected score if you play the game optimally? Okay, so there's a lot of things we can get. This is obviously not the exact statement that was in the problem, but it's kind of bullet points to give you the basic idea of what's being asked. And it's broken down in a way so that we can see kind of what some of the things we want to do. So you can keep drawing cards as long as you like. That means there's going to be some decisions involved as to when we choose to draw a card or when we decide to stop. If you ever draw a duplicate, game's over and you score 0. So we have a very clear point where we know that there might be no more payout to be had and there might be more risk. And we see very plainly is the expected score and play optimally. So that means what's going to happen on average, not necessarily every time, not guaranteed, but what's on average going to be what we expect to happen. Play optimally means we look at our different choices at each step and we make the selection based upon which one is going to have a likely better result. Okay. And of course, we're dealing with both probability and some mathematical expectation. In terms of programming, we need to keep track of which cards we've already drawn. The constraints of the problem are actually written such that I believe the maximum value on a card is the number 15. This was done intentionally so that you can actually keep track of which cards you've drawn in your hand in a bit mask. Notice the fact that you never, essentially if you draw a duplicate, that ends the game. So you're never going to have a situation where you've got more than one of any given value in your hand. That makes it really easy to keep track. That also tells us there's 65,536 states we need to keep track of. As a programming contest person, you're probably thinking about these things as you're reading over the problem and as you're thinking about your approach. This gives you some idea of how many states we're going to be looking through, how many different states we're going to remember, what things we're going to be keeping in memory, these kind of things. And we need to make decisions. We have to determine the expected result either way and make a decision that has a better expectation. So how do we do that? For each possible situation, and each possible situation meaning which cards we've drawn, determine the probability of getting each possible value on the next draw. Remember, if you have a bit mask indicating which cards you're holding in your hand, that also tells you which cards are remaining in the deck. Because we're given the composition of the deck to begin with, and we know which cards we've got in our hand, we know exactly how many of each value are left in the deck. From that, we can pretty easily calculate the probability for each possible card value on our next draw. And then we have to calculate the expected value from drawing versus the known value of stopping and choose accordingly. So at each step, if we stop playing, then we're going to score exactly what is the total of the cards in our hand. If we draw, what do we expect is going to be the value that we're going to win? We need to work backwards or recursively with memorization. Probably heard the term already, but memoization means you're doing recursion, but you're storing your data in some sort of a table or data structure so that if you've called your recursive function with a certain set of parameters already, you don't have to recalculate the whole thing. Now, the way I actually wrote my solution for this, and again, you can actually find solutions on the website already, of course, from the contest itself, is I started backwards and started with the situation of, okay, what if my hand has every card value in it already? Because in that case, it's obvious. And what I'm going to do is I'm going to stop playing because I know that whatever I pull next is going to be a duplicate. I'm going to stop playing and I know I can expect in that situation, I can expect that I'm going to just take the points I've got and that's the end of the game. Working backwards, if I'm missing any cards, I can calculate what's the chances that my next pull is going to be one of the cards that I'm missing. And because I'm working backwards, I've already calculated my expected value for those other situations. So I know the probability of each possible situation I'd be looking at. I know the expected value of each situation. And just like it's the multiplication of probability times payout, add them together. That's all you have to do here. And then I simply make the decision, do I go for it with the poll, or do I take the points I have? Whichever value is greater is the one I do. So even though the problem seems like there's a lot to unravel, if you take it step by step, going through the steps we have here, we're putting together a lot of different concepts we've gone over, but they all do work together. The other problem I want to talk about a little bit, and then we should have plenty of time at the end for questions, which is nice for anybody that wants to ask anything. Card draw game. This one is a little bit different. You draw 3 cards from a deck. The deck has cards in it. You're told what values of cards are in the deck and how many of them. The goal is to use those 3 cards to reach a specific target value. One might imagine in American casinos, some sort of a game where you're trying to reach 21 is very common. There could be any value in this problem. The actual value doesn't really matter that much. Now the rub is that after you draw your 3 cards, you get 1 chance to redraw any or all of your cards. Now, hopefully if you've been paying attention to this, you have a pretty good idea. Drawing 3 cards from a deck and seeing if you're at the target value or not, you can calculate the probability with a little bit of effort. Worst case, you can brute force through all of the possible draws that you get, count up how many of them actually hit the target value, divide by the total number of draws you get, which is number of cards, choose 3, and you divide. So you could do that. What makes it interesting is that you have the option to redraw some of your cards. You can keep your 3 cards, you can get rid of 1 and redraw it, you can get rid of 2 and redraw them, you can get rid of all 3 and redraw them. So we've got some choice here. We've actually got several choices we can look at. Of course, the question is, if you play optimally, what's your chance of winning the game? That is, what is your chance that the 3 cards you have in your hand at the end reach that target value? So first, we consider all the possibilities for our initial card draw. And the way the problem was written, the constraints are such that yes, you actually can more or less brute force through that. Since there's only so many different values of cards that could appear, for each of the 3 draws, you consider what if it is one of these, what if it's a 1, what if it's a 2, what if it's a 3, etc. And just keep track of how many you've pulled out of the deck. It is important that you keep track of what you've pulled out of the deck because in this case, we're looking at one of those scenarios that we talked about right at the top of this where they're dependent events. We're talking about card draws from a deck where they are not replaced. You do have to definitely realize that. So it is important to keep track of how many cards are left in the deck and which ones they are. So we consider all of those possibilities. And now we need to look at the probability of winning. What if we keep all 3? What if we redraw 1, redraw 2, or redraw all 3 of them? So we're going to go through again and we're going to consider all possibilities for redrawing. Again, looking at the constraints of the problem, which I don't have fully outlined here, but you can see that the constraints are small enough you can actually go through all of these and figure out for every possibility, what are you going to get? And then you determine how many to redraw based on which is most likely to win the game. So what you do, there's actually 8 different things you need to consider. I know it sounds like there might only be 3, but the question is which 1 card do we redraw or which 2 cards do we redraw? Another way to think about it is you have 3 cards in your hand. Each of those 3 cards you can either choose to keep or redraw. So that's 2 to the 3rd. So there's 8 different ways you can look at it. You calculate the probability for each of those 8 scenarios, and you pick the highest one, because whichever one is the highest is what you're going to do. That's all I've got for today. We went just over an hour for that, but we do have plenty of time for questions. If anybody has a question, wants me to go back and cover something else again, that's totally fine. If nobody does, I guess that might be a little disappointing, but that's okay too. But I'll stay on for a few minutes, and I'll keep my eye both on the questions window and on the chat window, so that if anybody wants some clarification, wants me to talk more about something else, wants to ask a question that's somewhat related to this topic, but perhaps is a little bit different, I'm happy to go over that also. Either way, thanks everyone, and I hope you had some fun, maybe learned something. As came up in the chat, I will say it in the presentation, yes, this slide deck is going to be published. The problem sets that I'm talking about are already available in the problem archive. I believe there is going to be a video of this presentation that's recorded and posted later. It should be in the forum thread somewhere. It'll probably take a few hours until that's ready. And oh, okay, yes, and I see in the chat there's also a link. If you come up with questions later on, you're welcome to post them in the forum. If you have questions now that you want me to answer while I'm online, please do ask them now in the chat, because I'm not actively checking the forum thread just yet. To be able to do this presentation, I can only have so many different windows open at once. I'll give it another, say, maybe 2 minutes or so, see if anybody has anything they want to ask. If not, then we'll get ready to call it a day. Regardless, I hope you've all had fun. Perhaps we'll do this again sometime. We'll talk about some other things. If you have actually, if you have topics that you would like me to talk about for a future presentation at some point that we might consider doing, feel free to mention that also. I do believe there are plans to continue doing presentations like this from various different contributors. So if there's something you want, ooh, okay. So if there is something you want to learn more about, feel free to let us know. Okay, so the question that just came in is probability and statistics used in real world development. That's a great question, actually. As with a lot of things, the answer is it depends. That's probably not a very satisfying answer though, so I guess I should give you more details. One thing I will say that I have actually observed, I've been doing software development in various different flavors professionally for about 20 years now. So I have seen a fair number of different scenarios. More often than not, I find that most software engineering, most programming, most development is actually remarkably simple. 80 to 90% of the stuff I see businesses dealing with is a whole lot of fetch data from someplace, do something to look at it, display it, let people edit it, and then store the data back. I saw another problem question come in, which I'll get to next. But so a lot of development really is fairly simple stuff, just about fetching data, saving data, storing data, printing data, importing data from someplace, exporting data somewhere else, displaying things nicely. That covers probably 80% of what happens in most businesses, realistically. So sometimes this stuff might seem irrelevant. Underneath the hood, however, though, this stuff may come up more often than you think. Probability and statistics comes up a lot in decision making. Comes up a lot in a lot of algorithms that do sort of heuristic-based things. Real-world algorithms like Google Maps, etc. Okay, so for folks that don't know, I did actually work for Google at one point in my past, so I have to be careful what I do and don't say about that. I never worked in maps, so I can't comment specifically on what they do. I wouldn't be able to actually comment on it anyway. But I would say just generally speaking, things like that, yeah, probability and statistics probably comes up quite a bit. What we call heuristic algorithms, which basically make guesses and try to look at what is most likely to be the correct answer first and spend more time on that and less time on things that are less likely to be the best answer. That's where you're going to see some probability and statistics come up. Where it comes up in businesses a lot, though, is simply in decision making, where statistics, you're going to look at, what's the average order size that our clients are placing. That can help you determine if there is, fake information coming through, orders that look like they're probably not real because they're either so small or so ridiculously large that they couldn't possibly be real. We talked about things like the bell curve, where the further you get away from the mean, the average, the less likely that is to happen. If you see that happening a whole lot, that's kind of a clue for you that maybe something is wrong. So these things do certainly come up. Okay, so I'm hoping that answers your question well enough for now. We can certainly go into deeper discussions about that on the forums or wherever if we want. But to make sure that okay, good, that did, thanks. Okay, and I do see the other question. Thank you, Harsh, for copying it to the chat also. In the birthday paradox problems, what about the probability of 3 people sharing the same birthday or K people having the same birthday? Okay, so that gets a little bit more interesting. I don't know if there's a good closed form formula for it right off the top of my head, but this is certainly where programming would come into it. You could certainly write a dynamic programming solution, and it would look something like, your state space would look like the number of people, the number of birthdays that are shared by n people for n equals 1, 2, 3, however many, and you would recurse on that. As you add each additional person, what's the probability that the new person coming into the room shares a birthday with, has the same birthday as 3 people already have, as 2 people already have, as 1 person already has? And you can recursively or dynamically build up to determine the probabilities for this. Again, I don't know if there's a good closed form formula. There might be. I apologize, I don't know that right off the top of my head. But again, that's where programming is fun. So kind of, we'll call that a kind of an open question. I would say, actually, if anybody has a good answer for that or has some code written, talk about it in the forum. So I think that could be actually very interesting. But it's certainly certainly something you could solve with programming. And it's actually funny, I have a problem I have not yet used in an SRM that almost is kind of sort of similar to that idea. Similar but different. I won't say more than that, just that's a little teaser. I don't want to give anything away, but if you actually tuned in for the presentation today, you know that you may see a problem that's sort of is kind of like that in the future. I hope that's enough of an answer for now. I don't want to, I'm not prepared to dig into enough of a rat hole on that one, but it gives you an idea of what you can kind of look into. And once again, I'll give it another, as probability values are between 0 and 1, such as fractions, so comparison of floats can be an issue. That's an excellent question. The short answer on that is yes, it can be an issue. The longer answer is, for purposes that you care about, in programming contests, probably not going to be an issue. But it depends. It depends on what the question is asking. If the question is asking which option is optimal, and specifically wants to know which option it is, then you better be sure that you know which probability is greater. In which case, thinking about precision and stuff like that is important. If the question is merely asking what is the probability that you're going to win, because the system already takes into account a small epsilon value of usually 1e minus 9, because the system's taking that into account already, and you're only looking for the probability of winning, not necessarily which option is the best one, then the comparison doesn't really matter. Because even if you're off by 1e minus 12 on which option is better, the value that you calculate for the probability is still going to be correct. In cases where, so first thing I'll say, as a problem writer, I probably would not write a problem where I asked someone to select the best option, especially because if there was a situation where the probabilities could be close enough like that, then obviously we've got an issue. Or if I were intentionally writing the problem that way, I'm not going to say I've never done this. People hate me when I do it. And I really don't want people to hate me. I do want people to think and be challenged by problems. And I do have fun writing some more challenging problems, but I'm not doing it to make people angry, I promise. There are cases where problems are specifically written to make people think about that issue. It wasn't specifically a probability question, but the question was actually, trying to remember how I phrased it. It was essentially about figuring out Pythagorean distances on a plane, and the constraints were specifically written so that in certain cases you would get large enough values that if you were calculating things using floats, you could potentially get into trouble. And in fact, a lot of people failed the problem from that. Rather, the point of the problem, though, was to make sure that you did all of your calculations in integers by not taking the square root of anything. When we're talking about probability values that are fractions, one option, if you had to get around that issue and be really, really sure, would be to write up a data type for a fraction rather than using floats, which, yes, I realize is a lot of heavy lifting, and there's a reason we don't usually write problems that are going to have an issue with that. But obviously comparing fractions to each other is a little bit easier to do than comparing floats. I'm sure you know all the ways to do that already, probably. But yeah, so in theory, yes, it could be an issue. In reality, for most problems, And even for most real world situations, if the difference between two options is 0.000000001, you're probably not going to care in the real world. And so in actual scenarios that you're going to face in real life, probably not going to matter. I'm hoping that answers that well enough. Anybody else have a question they would like to ask? We'll give it another minute or two. At any rate, I will obviously continue if anybody asks something, but assuming there are no other questions, I hope everybody's at least had fun. And again, do post your thoughts on other content you'd like to see, other questions you have. If there are specific SRM problems that you're very interested in, I would say probably I would shy away from most of the Division I hards and possibly even a lot of the mediums, just because trying to explain them in a online webinar format sounds like it might be not very practical and might be more confusing and frustrating to everybody involved, myself included. But if there's any kind of medium difficulty problems that you specifically want to see worked out and get some insights on how one might go about solving them, or a specific type of problem that you think is worth talking about, certainly let us know, and we'll see about putting together a presentation to talk about those and some of the underlying concepts. Let's see. Machine learning equals probability and statistics. Yes and no. Machine learning is a whole nother concept. It builds upon probability and statistics quite a bit. I'll say more or less yes. We'll leave it at that. That machine learning is a whole nother topic and a rat hole I definitely don't want to get into today, only because we'll never get out of it. That's also more applicable more to a lot of the marathon contests and some of the hardcore data science contests we have with some of our real world client data. But I do think that's definitely an interesting discussion. And if we don't already have one scheduled, we may even have already thought about it. Something about machine learning and data science certainly would be an interesting presentation to do. Not sure who would do that one, whether it would be me or somebody else. There's a lot of us that could probably do an interesting discussion on it. Yeah, all right. Again, I'll make a few quick edits to this slide deck before posting it, before sharing it online and posting it with everybody, just to make sure that I correct a few little typos and clarify some things that as I was going through this with you all today, I realized may not have been clear or may have been some mistakes. We obviously don't want to have those up. And yeah, it'll be up to probably Harshit or somebody on that side to make sure that the video gets posted. Again, do feel free to post your questions in the forum. I will do my best to respond to them as I see them come in, if anybody has a question after the fact. But other than that, I hope everybody has a good rest of your day. For those of you that are kind of stuck at home, not able to go to work, not really able to go out anywhere lately, which is a lot of us, I wish you all the best and have fun being online. All right, everybody, take it easy.
Thanks, everyone. Thanks, Erinn.
Thanks, Harsh.